Hey, welcome back to Fat Mama Physics. So hopefully at this point you know what de Broglie wavelength is, this relationship, and just to re-emphasize, it's not in your data booklet, so it's something that we want to be very careful of and be able to know how to apply. So essentially what this video I want to do is I want to show you when a particle or any sort of mass tends to behave as a wave and when does it not. So let's take a look at example 1 and 2 will be the focus of this question. Okay, so let's begin. Calculate the Broglie wavelength for a baseball traveling at 40 meters per second. So let's use de Broglie's wavelength and figure this one out. We know the momentum is the mass times velocity of a particle. So if we put in this mass and put in, and the speed over here as mv with Planck's constant, which is in your data booklet, then we are going to find the following. I get 1.183 times 10 to the power of negative 34 meters, and rounding up to 2 sig figs, 1.2 times 10 to the power negative 34 meters. And yes, you are thinking that is a very, very, very tiny wavelength. So not very wave-like at all, are we? Or a baseball for that matter. But if we compare that with the de Broglie wavelength of an electron traveling at 1% of the speed of light, let's see what that looks like. So again, we have de Broglie wavelength, which is h over mv, in which h is your Planck's constant. And the mass of an electron is also in your data booklet, 9.11 times 10 to the power of negative 31 kilograms. And the speed of light is 0.01 times 3 times 10 to the power of 8 meters per second for the speed of light. So after we do that, we get 2.4259 times 10 to the power negative 10 meters, which is relatively 2.4. Let's see, 3 sig figs? 3 sig figs times 10 to the power of negative 10 meters. And notice that this is relatively the size of an atom. So that's 10 to the power of negative 10 meters. Something like an electron is going to behave more like a wave versus something like a baseball. So here we can answer this question. The particle, the more the particle behaves like a wave. So yes, the less mass of the particle is, the more the particle behaves like a wave. So this much more applies more to the subatomic scale as opposed to something big scale like every day. Imagine, seeing your friends as a wave. That doesn't work. It doesn't it doesn't quite make sense. So that is the comparison. Okay. All right, so that's going to be the conclusion of this video for these examples. In the next few videos, we are going to look at accelerating an electron, find the de Broglie wavelength of it, and showing this relationship that is down here. Okay, so I wish you the best of luck, and I hope you learned something from this video. Thank you for watching. Fat Mama Physics signing out.